സാറിന്റെ സൗണ്ട് കേൾക്കുന്നില്ലല്ലോ സാർ.
Just this.
ഓക്കെ സാർ.
ഇന്നലെ ചെയ്ത ഫയൽ എവിടെ നോക്കാം.
ഓക്കെ സാർ.
Yes. Yesterday we were discussing regression. Now this was the data. We have seen that the first step is to create a scatter plot and convince ourselves that a satisfactory linear trend is observed in the data. Okay, then my model is the name of the object we have created. LM is the name of the function y tilde x. What is y? Y can be named as dependent variable or response variable or regressor variable, etc. X is called the explanatory variable. Okay, and if you want to see the summary of the regression, you are getting this one. Okay, today we will discuss so many things related to this because this is an important topic for all. Okay, and we will look the regression problem in detail. In detail, we will look at it. Okay. Now, what is effects? Effectively, this one is to get a satisfactory relation between two variables. Okay, y is equal to alpha plus beta x. And we know x is under the control of the researcher. X is under the control of the researcher. Y is not at all. Okay, using x, we want to predict y. We want to explain the relation between x and y. Okay, therefore naturally there will be some error. Therefore, alpha plus beta x or yi, alpha plus beta xi plus error. You are predicting something. Very rarely it can be equal to the actual value of y. Some error will be there. Okay, now what is this error? For the time being, we assume that EIs are independent. That is, error involved in one value is not at all depending on other one. With the average value 0 and variance constant. Variance constant. Whether it is for x1 or x2, etc., the variance is constant. Okay, therefore this part is like that. Okay, for example, suppose x is the height. X is the height, and you want to estimate the weight. Actually, what we are doing here, we want to find average weight for a given height. That is what we are estimating. Average weight for a given height. That is alpha plus beta into height. If you know the height, what is the average weight? What is average weight? For example, if you take all the students in the campus with the 155 centimeters height, do they have same weight? Never. Okay, you take all the students with the 150 centimeter height, their weight will be something like this. Okay, some may have 45 kilograms, some may have 78 kilograms, like that. What is the average weight of students? What is the average weight of students whose height is 155 centimeter? Okay, this is what we want to find. Okay, now very simple thing actually, very simple thing. We have seen there should be some policy. There should be some policy to estimate alpha and beta. Alpha and beta are estimated using principle of least squares. Okay. If we use the notation Sxx is equal to summation x minus x bar the whole square Syy summation y minus y bar the whole square and Sxy x and y. There was summation x minus x bar into y minus y bar. Beautiful notation. Sxx, Syy, Sxy, x minus x bar, y minus y bar. In the place of y, you take x, then x minus x bar and x minus x bar, you will get this one. In the place of x, if you take y, y minus y bar and y minus y bar, you will get this one. Okay. Therefore, fitting the model. Fitting the model means we have to find the best values of alpha and beta. Alpha and beta using principle of least squares. Okay. And next one is we have to estimate error variance. What do you mean by error? Which couldn't estimate. Okay, y is the actual value, y cap is the estimated value, therefore this is known as error. Another name is residual, something remaining there. Error variance, what? Okay, then using principle of least squares, you have to minimize summation y minus y cap the whole square. By the method of calculus, the best value for beta is Sxy by Sxx. And the best value of alpha is alpha cap. Okay, this is relation. Y is equal to alpha plus beta x. From this, what is alpha? Alpha cap is y bar minus beta cap into x bar. These are the best values of alpha and beta. Okay, and error variance. An estimate of error variance sigma cap square is 1 by n minus 2 summation yi minus yi cap square. On simplification, you will get 1 by n minus 2. This is yi cap. Yi cap is alpha cap plus beta cap into xi. Substitute the values of alpha cap and beta cap. You will get this as Syy minus s square xy divided by Sxx. Okay. Again, one more point I have to highlight, because all those things are coming there. Now we consider yi minus y bar. The difference between the observed values and the mean. Okay. Then you add 0 with this. yi minus y bar plus yi cap minus yi cap. This technique is called adding 0. This is 0. Okay. Then this you write as yi minus yi cap plus yi cap minus y bar. Then you take square of these things. Then you can see that the product term will be 0. The product term will be 0. Therefore, sigma yi minus y bar the whole square is equal to sigma yi minus yi cap the whole square plus sigma yi cap minus y bar the whole square. What is this one? yi minus y bar. Observed value minus mean. Okay. What is the formula for variance? Formula for variance is yi minus y bar the whole square by n minus 1. Therefore, this one can be taken as the numerator part of the variance. This is called a total sum of squares. Total sum of squares. This is equal to, what about this one? yi is the observed value. yi cap is the estimated value. Therefore, this is residual. Residual. Therefore, this is called a residual sum of squares. Plus yi cap and y bar. Okay, yi cap is the estimated value. Y bar is the overall mean. Okay, this is called a regression sum of squares. Regression sum of squares. Therefore, this is the partition of total sum of squares into two. One is which is not explainable by the model. That is what is called residual. This is explained by the model. Suppose this is equal to 100. Suppose this is the case. What is the meaning? The regression explains 98% of the variation in y. The regression model is a very good model which can explain 98% variation contained in y. That means what? Our model is a good model. Suppose this is the case. Residual is more, unexplained part is more. Unexplained part is more. That means the regression model can explain only 2%. That means the regression is bad one. Therefore, this is the technique to see whether our model is a good model or bad model. Then R square is defined as coefficient of determination. Coefficient of determination. This is what? Sum of squares due to regression divided by sum of squares due to total. Now in this case, what is that? 98 by 100. That is 0.98. That means what? 98% of the variation in y is explainable by the regression model. That is why this is called the coefficient of determination. Coefficient of determination. And this will give you a better idea about the validity of the model. If this value is very close to 1, definitely this SSREG is less than or equal to SS dot. Therefore, this will be less than or equal to 1. Sum of squares can never be negative. Therefore, 0 less than or equal to R square less than or equal to 1. If it is very close to 1 means what? Our model is a good model. For practical purpose, if the model can explain at least 70% of the variation contained in the regressor variable, that model can be an acceptable model. Okay? Then this one will be higher. Okay, I will discuss that when we discuss multiple regression. Okay, because then also I have to explain. Where is our R? Yes, here you can see multiple R square, 0.9182. 0.9182. That means what? 91.8% of the variation contained in Y is explained by this model. Now here you can see adjusted R square. That is also an important person. Adjusted R square. Suppose you want to conduct a study in your campus, for example, physics department. Okay, the new batch is going to come now. After 2 semesters, you want to estimate the marks of the students after MSc. That is why you cannot simply close your eyes and estimate. You need some supporting variables. Marks for BSc, marks for +2, marks for SLC, okay, and gender. You may think economic activity of the father, age of the father, age of the mother, where is the living place of the students, whether coming from home or living in the hostel. If it is in hostel, whether living in a single room or in a room so many students are living. If so many students are living, what about the marks of those students? What about the number of hours the student is studying? You may think that all these variables are important for first semester mark, second semester mark, etc. You are getting a very, very complicated model. Suppose you are taking 40 variables like this. K is 40. In every case, you can see that the value of R square is increasing. Value of R square is increasing. Suppose in the first case, it is 0.9183. Second one, it may be 0.918301. When you add one more variable, it may be 9831. When you add one more variable, it may be 9184. It will be increasing. It will never decrease. It will never decrease. Remember that when you add more and more variables, the model will be more and more complicated. The workload is very heavy. You have to collect all the data. You have to collect the BSc marks, plus 2 marks, SLC marks, whether the student is a boy or girl, what is the job of the mother, what is the job of the father, what is the age of the father, what is the age of the mother, whether she is living in the hostel or coming from the home, a day scholar or a hostel mate, something like so, so many things you have to collect. Okay? R square will never decrease. When you add more and more variable, R square will be always increasing. R square will be always increasing. Okay? But you want to know whether this change is significant or not. If the addition of one variable is not at all helping us, why should we add that variable? Why should we add that variable? Okay, we need not add that variable if we are getting same information with the 10 variables and 11 variables. What's the purpose of adding the 11th variable? Okay, therefore the suggested R square is R square adjusted with the number of explanatory variable. Okay, therefore adjusted R square is 1 minus R square into n minus 1 divided by n minus k minus 1. N minus 1 divided by n minus k minus 1, where k is the number of variables. K is the number of variables. And if the number of variables more and more, you can see this one will be smaller and smaller. Therefore, R square adjusted will be slightly less than R square. Slightly less than R square. Okay. Therefore, for practical purposes, even though R square is a good indicator, a good measure, okay, and since one R square, adjusted R square is the value adjusted for the bias in the number of variables, it is always advisable to take a decision based on adjusted R square. Okay. Now here you can see 0.9182, 0.908. Now let us do another model. My model 1. This is equal to LM y tilde 1. Y tilde 1. Summary, my model 1. My model 1. Now you will get you see here we have not used any variable. That is why tilde 1. Tilde 1 means we have not used any variable. Okay. That means what? The estimate of y is y bar. The estimate of y is y bar. Okay. Then here we have used one variable x, and multiple R square is 0.9182 and adjusted R square is 0.908. If you can see, it is also 0.91. It is also 0.91. Okay, it is also 0.91 approximately. Okay, that means what? Even that variable doesn't have that much influence in this one. Okay, to know more about that, you consider analysis of variance. ANOVA, my model. ANOVA, my model. It's a wonderful technique developed by Professor R.A. Fisher. This is residual sum of square. Residual sum of square. You can see it is very small. It is very small. And this is sum of squares due to regression. Okay. Therefore, the contribution to total sum of squares is more from residual sum of squares due to regression. Sum of squares due to regression. What is our assumption? The model is not good. The model is not good. What is the p-value? Very small, less than 0.05. That means what? The sample evidences are not supporting the alternate hypothesis. Null hypothesis. That means what? The regression is good. The regression is good. We can calculate these values directly. These values directly using this formula. Using this formula. Okay. That is yi cap minus y bar the whole square. That is sum of squares due to regression. This is sum of squares due to residuals. And this is total sum of squares. Yi minus y bar the whole square. Okay. You can try because all those things are very simple. Okay. Suppose you want to predict. You want to predict. What is to be done? Predict model. That's all. Predict. P-R-E-D-I-C-T. Predict. Name of the model. My model. My model. Yeah. These are the predicted values. These are the predicted values. Suppose you want to create a table. What is to be done? Data frame. Data frame x comma y comma. Let me put this as PR. PR. X comma y comma PR. Okay. You will get a table. You can see x, y. Observed value is 2.18. Predicted value is 2.02, 2.06, 2.28, 2.54, 2.37, 2.61, 2.99, 3.67, 3.34, 3.25, 3.51. Okay. These are the observed values and these are the predicted values. You can plot these curves. That is plot y comma PR, plot y comma PR. Yeah, you can see y comma PR. This is the observed value. This is a predicted value. Okay, almost diagonal line, no? Almost diagonal line. That means what? The model is satisfactory. Okay, the model is a satisfactory one. Suppose you want to predict for another value. What is to be done? You write my data. My data is equal to data dot frame. That is important. Data dot frame. You can give x is equal to what is to be done 4.9. X is equal to 4.9. Then you have to write predict. Predict. What's the name of our model? My model. My model and my data. My data. You can do these things even without that, no problem. 4.486. Let us see whether that is correct or not. What is our model? Our model is This is our model. Intercept 0.16363, 0.16363, 16363. Coefficient of x is 0.88231. The model is 0.16363 plus 0.88231x. Let us substitute here. Therefore, yy is equal to 0.16363 plus 0.88231 multiplied by 4.9. 4.9. To see that value, yy. You should get the previous value. Yeah. 4.4869, 0.88231, 0.88231, 16363, 16363. Okay. A small difference is there. However, the first four decimals are correct. 4.486, 4.4869. Okay. If you only this, maybe some rounding error is there. This is how to predict the value of the regressor variable or dependent variable for other values. Suppose you have to do it for so many things. My data is data frame C brackets. C bracket 4.9, 5.2 and 6. Okay. What is unexpected symbol? Can you point out the mistake? Here the bracket is not closed. Ten rows. Okay, no problem. Warning message. Yes. Therefore, this is the estimated value for x is equal to 4.9, x is equal to 5.2, x is equal to 6. X is equal to 6. Okay. Therefore, these are the applications of regression. Okay. To predict the value of one variable when the value of the other variable is known. What is the weight when the height is given? What should be the dosage when the age of the baby is given? Okay, like that. If you want to know fitted value, another one is fitted. This is also a function. Fitted bracket my model. So many ways you can use fitted my model. These are the values correspond. This one we got here 2.016478. Predict and fitted. Both are doing the same work. Okay. And if you want to know the residuals, it is coming already. Residuals bracket my model. What is residual? Actual value minus estimated value. Okay. These are the residuals. 0.16, negative 0.22, 0.17. They are very small now. but here it is little bit. Okay. Now you can see one wonderful relation. Wonderful relation. R is equal to correlation between X and Y and R into R. Point 9182.201. Here you can see 0.9182. For simple regression, multiple R square is nothing but coefficient of correlation square of the correlation coefficients. Okay, these are some simple points about the simple regression. Now, here you are having only one explanatory variable. In some cases, we may need more variables to predict a variable Y. Yesterday, we have seen number of examples. Crop. Crop depends on seed, fertility, pesticide, humidity, knowledge of the farmer, that, this, etc. Okay? Therefore, naturally, we can go for multiple regression model. Multiple regression model. What is the only difference? Here you are having more explanatory variables. More explanatory variables. Okay? So what is the model here? Y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus etc. beta k xk. x1, x2, etc. xk are the explanatory variables, and y is a regressor variable or response variable. Okay. Very rarely we use the word dependent variable. Very rarely. Okay. Now, what are the assumptions about x1, x2, xk? They are independent. They are independent. Okay. Now, if you want, you can add one EI. Okay. And what about the assumption of EI? Expectation of EI is equal to 0 and variance is constant. Okay. Therefore, given x1, x2, etc. xk, what is the value of y? What is the value of y? That's the first question. Okay. And number of books are available, number of articles are available. With the ideas you are getting from this discussion, you read some books, some articles, you can get more. Okay. I had sent a data file to you. Please take that data file. Mul 1 you can take. Mul 1, let me check. Yeah, Mul 1 you can take. Mul 1 you can take. Mul 1. Import from Excel. You can browse. It is very easy. No C, etc., slash, etc., nothing needed. RStudio is very user friendly. Mul 1. Data is available. Data is available. Okay. Take a new file, attach. Attach mul underscore 1. Okay. If you want to see, type the name of the file. Yeah. The data is available here. Then my mul1. That is my multiple regression 1. LM finished. LM y tilde. Here we write x1 plus x2 plus x3. That is all. x1 plus x2 plus x3. Capital Y. That is why I have C. Okay. We will not use comma. We will use plus sign. Okay. If you want, you can specify data also. Data is equal to mul1. As before, if you want to see the results, my mul1. My mul1. Yeah. Result is coming here. Result is coming here. If you want to see more results, summary. Summary my mul1. If you simply type my mul1, you will get only the coefficients. If you use the function summary, it will give you testing results, etc. Here it will give you only the coefficients. Minus 0.1954, 0.2115, 0.1251, 0.5986, only that. Only that. Now, here you can see multiple R square is 0.9831. Adjusted R square is slightly less than that. Slightly less than that. Here you can see some stars. What is the meaning of that one? It is doing so many things for us. Without our request, R is doing so many things. What is our model here? Y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3. This is the model. It will test whether beta naught is 0 or beta naught is not equal to 0. Beta 1 is 0, beta 1 not equal to 0. Beta 2 0, beta 2 not equal to 0. Beta 3 0, beta 3 not equal to 0. Suppose you reject H naught. That means what? This beta naught is a must in the model. Suppose you accept this H naught. That means what? Beta 1 is 0. That means what? Variable x1 is useless. Variable x1 is useless to predict y. Therefore, the model is only this much. The model is only this much. Suppose you accept H naught. Beta 2 is 0. Then the model is only this much. What is the meaning of that? The information we can get from three variables, x1, x2, x3, can be available from x3 alone. Life is very simple. You need to concentrate only on one variable x3. For the final analysis, you need not worry about x1 and x2. x1 and x2. That is the meaning of this star. This means what? x2 is an important variable. Why? The p-value is less than 0.05. That means what? H naught is rejected. Beta 2 is equal to 0 is rejected. That is, beta 2 is not equal to 0. 0.004 less than 0.05. That is, beta 3 is equal to 0 is rejected. Beta 3 is equal to 0 is rejected. That means what? X3 is an important variable. X3 is an important variable. But here p-value is very, very high compared to 0.05. That means what? Beta 1 is equal to 0 is accepted. Okay, and I will show you again. Without x1, without x1, my multi 2, my multi 2, my multiple regression 2. Here I am using only two variables. Now you will be really surprised. You see, here 0.9831. With the three variables, 98% of the variation in y is explained by the model. Here 97%. 97% could be explained by the regression. Here you can see all the two variables are important. All the two variables are important. And here you can see adjusted R square is very close to R square. 9797, 9752. Here 9831, 9768. This is how we will see whether a variable is important or not. That is what I told you yesterday. Suppose you want to take 300 observations or 400 observations like that. You conduct a finite study first, taking 30 observations or 40 observations, and check what are the important variables. Okay? Again, you consider other data sets. I have given one more data set. Where is the other data set? Yeah, results. Oh, it is not, I think I have not given this one. We can do this. It is a resident data set. Data empty cards. It's a wonderful data set. If you want to know more about that, help to empty cards. Yeah. motor trend car road test, empty cars. The data was extracted from 1974 motor trend US magazine, etc., etc. The data frame with the 32 observations on 11 variables: miles per gallon, number of cylinders, displacement, horsepower, rear axle ratio, etc., etc. Okay. What is the variable of our interest? Miles per gallon. Okay. How many miles we can ride with 1 gallon of fuel? Okay. Suppose you take a model, my one. My one is equal to LM MPG tilde HP. Data is equal to MP cars. Data is equal to MP cars. Summary, my one. Because I will do so many analysis. You can see multiple R square is only 0.60. That is only 60% of the variation. Only 60% of the variation could be explained by the variable HP. Okay? Then let us take my 2. Then you will get more ideas. What will happen when we add more and more independent variables? My 2 is equal to HP plus weight. Weight of the car. Actually, there is also variable which can influence the mileage. Yeah, 82%. 82%. Here you can see, open your eyes and see. The coefficient is negative. That means what? As the weight of the car increases, miles per gallon decreases naturally. Because of bigger weight, the car has to pull all this weight. Okay? Now I will teach you wonderful techniques. Selection of variables. There are so many packages available. First method is forward selection method. What is a forward selection method? You are having so many variables here. X1, X2, etc. Xk. First you will select the most important variable, XR. Then using some criteria, you will select another variable, XS. Then another variable, XT. Now you find that all other variables are not important. Therefore, you will select variables one by one using some criteria. Don't worry about that criteria. Some mathematics is there involved. This is called forward selection method. Second one is, this is something like that. Suppose you are going to a shopping complex. and this is your basket. You find some item, important item, you will put that into your basket. Another one, you put excess. Another one, you put third item. Then you find that all the important purchase is over and you are going back. Second one is backward selection item. Backward method. Suppose your little son is selecting so many items. He will take a biscuit, he will take a chocolate, he will take that, this, etc. And he is coming with a full basket. You look at this one, throw away. Don't, no ice cream nowadays. You throw away. You throw away. You remove bad items. And finally, you will have only important items in your basket. Here you are starting with all items and you will remove, you will delete the unimportant items, and finally only the important variables will survive. Next one is both. You will add and delete, add and delete, add and delete. Here you are adding, here you are deleting. Here looking at the importance of variables, you may add or you may delete. Okay, and finally you will get only the important variables to regress y. Okay, for this you may need a package. You may need a package. OLS RR. OLS RR. OLS RR. Ordinary least square regression that you need. You have to install a package. Click on package. Click on package. Click on install. Okay, I will not do that because it is already there in my laptop. It will come. Yeah, it is there. Click on OLSRR. Click on OLSRR and install. Install. That's all. OLSRR install. Yes. I will paste with my first example. Library OLSRR. You see, it's a wonderful package. Wonderful package. OLSRR. If you want, you can get details. Help OLSRR. Help OLSRR. Yeah, OLSRR package. Tools for teaching and learning, OLS regression. Okay. And see the README on GitHub. You have to go to some other place. Package, OLSR version, etc. Okay. Then you use this function. OLS step on possible my multi one. We have no power to change ordinary least square step all possible. What do you mean all possible? It will take one variable at a time. It will take two variables at a time. It will take all the three variables. Now you will see the output, wonderful output you will get. My multi one. Yes. If you take x1 alone, r square is 0.94. R square is 0.94. X3 alone, 0.93. X2 alone, 0.47. If you use X2 and X3 to predict Y, 0.9797. X1 and X3, 0.9643. X1 and X2, 0.9518. If you use all the three variables, X1, X2, X3, it is 0.98. 0.98. That is what we got here, 9831. .9831. That is what you are getting here also. 0.9831. From this, if you are happy with the 94 percentage, you just use X1, finished. You just use X1. It is Malo CP Sankar. Malo is name of a mathematician. Okay, he has developed a criteria called CP criterion. Okay, if you want to know the details, when you get a time, you just write Malo's CP criterion. Malo's CP, yeah, Malo CP in regression. Malo CP compares the precision and the bias of the full model to models with a subset of the predictors, etc. You will get. Okay? It will give you. It will take the full model means what? Model with all variables. With a subset of the predictors means what? It will take only a part of the total variables. And it will check whether the subset contains very good information. Okay. If you are happy with the 97 percentage, you take only two variables x2 and x3. That's what we got somewhere here. X2 and x3 we have taken. Yeah, 0.9797. 0.9797. That's what you are getting here also. 0.9797. It gives you, if you sit with a calculator, you will take at least 3 days to do this work. Because so many calculations are there. So many calculations are there. But R is doing. Okay. Then OLS step best subset. My multi one. My multi one. My multi one. Yeah. It is giving x1, x2, x3, x1, x2, x3. These are the best predictors. Okay. Y is the dependent variable. Okay. Actually, yeah. It gives R square. Model 1 is this one, only using x1. We have seen it before. Using x1, it is 9.9463. That's what you are getting here. x2 and x3, 0.9797. x1, x2, x3, 0.9831. Okay? And adjusted R square, predicted R square, CP value. AIC is nowadays important thing. AIC, it is archaic information criteria. Archaic is a Japanese statistician. I'm not sure whether he's a statistician or a mathematician. Don't worry about the scientist. Let us use a general term. Scientist is a very old man, and it is very motivating. Yeah, archaic information criteria. Archaic info. Yeah, this is that man. I should not say man. This is that great man. Okay, and this work is very recent work. Yeah, this is his photo. Yeah. Archaic info. Before it was an information criterion. Okay. Before it was known as an information criterion. Okay. Then when others started learning the process and understanding the importance of this criterion, this A, they have given his name archaic. Archaic information criterion, Kurotobu Archaic. Okay. In 1971. And some mathematics is there. Little bit mathematics is there. And another one is Bayesian information criterion, BIC. BIC. Okay. Information means what? Just understand like this. What information is contained in that? Or what loss of information you can take anyway, no problem. Okay. Therefore, this is given SBIC, Savas Base Information Criteria. Everything is given here. And you look at the one which you can accept. If you are happy with the 94%, you take only one variable, finished. If you need 98%, you take x2 and x3, finished. If you take all the variables, and if you are ready to spend your time and money, etc., you take 3 variables so that you will get a model which can explain 98% of the variation contained in the variable y. Okay. OLS step forward, AIC. AIC means archaic information criterion. My multi one. All the details you want. Okay, no problem. It will give you all the details. It will give you all the details. What is warning message? All the details. You are going to get a very big table. Forward selection method. X1, X2, X3. In the beginning, it is using no variables. Archaic information criteria is 65. It is taking only X1, 32, X3, 33, X2, 59. What is the meaning? The least value is the important thing. Therefore, 32 is least. Therefore, it will take a plus means what it is adding. Plus means what it is adding. Therefore, it is adding X1 from X1, X2, X3. From these 3 variables, it is taking 1 variable. Again, it is doing. Then it is looking at the other values. AIC is 29 for X3, 32. 29 is the least. It is adding X3. Then It is finding the regression for y using two variables now, x1 and x3. Then x2, 22. It is adding x2 also. Therefore, x1, x2, x3. R square 0.992. R 0.992. R square is 0.9831. Adjusted R square is this. Predicted R square is this. ANOVA. Okay, regression sum of squares. We have discussed all these things. Residual sum of squares. Okay, parameter estimates. Intercept. Coefficient of x1, coefficient of x3, etc. Selection summary. Some warning messages are there, don't mind. Okay. Therefore, when x1 is selected, AIC is 32. When x2 is x3 is selected, AIC is decreased to 29. And R square increased. R square increased. Okay. When x2 is also selected, then AIC value is further decreased to 22. Okay. Therefore, using these techniques, you can select important variables. Important variables. Okay. Then similar things you can do for forward also. OLS step forward. OLS step forward. My multi one. If you want details, you have to ask. You have to ask. Yeah. Now, what happens? OLS step forward brackets my multi one. My multi one details is equal to true. Warning message is deprecated. Oh, P. Oh, that is the old one. You have to use this one. Okay. Okay, no problem. Every time they are making some upgradation in the package. Yeah. OLS step forward underscore P. We have started from here. Forward selection method. X1, X2, X3. Step 1. X1 is taken. These are the detail. R square is 0.946. Again, this is the regression with the X1 only. Then it is taking X3. R square is 0.964. This is the model with the X1 and X3. Beta naught plus, beta 1 X1 plus, beta 3 X3. Then X2 is added. X1 plus X2 plus X3. Okay. Same thing backwards. Final result will be same. Final result will be same. Yeah. Backward backward elimination method. It is starting with x1, x2, x3. We are eliminating variables. No more variables, that is the condition. Okay? No variables can be removed. Then you can use both. Both mean what? Adding and deleting. Adding and deleting. Yeah, from here, stepwise selection method. We are selecting variables based on value. First, x1 is the most important value. This is a regression using x1 plus x3. It is adding the third variable. It is adding x2 also. The final model is this. This is the final model output. Added or removed. x1 addition, x3 addition, x2 addition. Okay? This is the selection of variables for regression analysis. There are three methods: forward method, forward addition method, backward elimination method, and forward and backwards stepwise regression. Okay, we just know the technique. The system will do all the work for you. You just write LM y tilde x1 plus x2 plus x3 and just write my summary. Finished. Finished. Here you see this variable is not important because there is no star. There is no star. Star means the corresponding variable is important. No star means no superstar. He is not a Rajinikanth. Okay? Therefore, you can delete this variable from the analysis. We have done a very big thing. If you have some doubts, you please ask.
Sir,
Yeah.
ഇവിടെ അക്കേക്ക് ഇൻഫർമേഷൻ ക്രൈറ്റീരിയ എന്ന് പറഞ്ഞിട്ടൊരു വാല്യൂ കാണിച്ചില്ലേ? അത് ഈ മോഡലിന്റെ ക്വാളിറ്റി ആണോ കാണിക്കുന്നത്?
അക്കേക്ക് ഇൻഫർമേഷൻ ക്രൈറ്റീരിയ അതായത് എവിടുന്ന് ഞാൻ തുടങ്ങും?
അല്ല സാർ, അങ്ങനെ ഞാൻ ഉദ്ദേശിച്ചത് ആ വാല്യൂ കൂടുതലായിരിക്കണോ കുറവായിരിക്കണോ?
കുറവായിരിക്കണം. That is must. കുറവായിരിക്കണം. That is where is that? ഏറ്റവും ചെറിയ AIC വാല്യൂ ഉള്ള ആളാണ് ഏറ്റവും നല്ല മോഡൽ.
ഓക്കെ ഓക്കെ.
എൻട്രോപ്പി. Archaic information criterion. It combines wonderful thing. ഇത് അടുത്ത കാലത്താണ് അത് ഡെവലപ്പ് ആയത്, ഈ കമ്പ്യൂട്ടർ ടെക്നോളജി വന്നപ്പോൾ. You sir, please see whether that outside Kerala candidate is there today.
No sir, he is not here today.
Okay. അപ്പോൾ ഈ അടുത്ത കാലത്താണ് ശരിക്കും ഈ കമ്പ്യൂട്ടർ ടെക്നോളജി നോക്കാൻ ഒരുപാട് വർക്ക് വരുന്നുണ്ട് അതിൽ. ഇതാണ് ഫോർമുല -2 log likelihood 2k plus എക്സെട്ര എന്നുള്ള സംഗതിയാണ്. ഓക്കെ, അപ്പൊ ഇത് നമുക്ക് അറിയേണ്ട സംഗതി ഇത്രയേ ഉള്ളൂ. റിലേറ്റീവ് ഡിഫറൻസ് ഏറ്റവും മിനിമം AIC is a score for the best model. മിനിമം AIC is a score for the best model. അപ്പൊ AIC ഓരോ കേസിലും AIC കണ്ടുപിടിക്കുക. നമ്മൾ കണ്ടുപിടിക്കേണ്ട പാക്കേജ് കണ്ടുപിടിച്ചോളൂ. അതിന്റെ എപ്പോഴാണ് മിനിമം വരുന്നത് ആ മോഡലായിരിക്കും ഏറ്റവും നല്ല മോഡൽ. അവൈലബിൾ മോഡൽസിൽ ഏറ്റവും നല്ല മോഡൽസ് അതായിരിക്കും. ഓക്കെ, ഇവിടെ തന്നെ നോക്കിയാൽ നമുക്കറിയാം. AIC കണ്ടോ, X1 മാത്രം എടുക്കുമ്പോൾ 32, X3 കൂടെ എടുത്തപ്പം 29, X2 കൂടെ ചേർത്തപ്പോൾ 22. ആകെ 3 വേരിയബിളേ ഉള്ളൂ. അപ്പൊ 32 3 കുറഞ്ഞു 7 കുറഞ്ഞു. ഓക്കെ, ദാറ്റ് ഇസ് എ ടെക്നിക്.
ഓക്കെ സർ.
ഇത് നമുക്കിപ്പോ ഇത് ചെയ്യുമ്പോൾ മനസ്സിലാവും. വേറെ ഒരു പ്രോബ്ലം ചെയ്ത് കാണിച്ചു തരാം. ഡാറ്റ empty cards. You want some rest? ഹലോ, പറഞ്ഞോളൂ, മടിക്കൊന്നും വേണ്ട. 10 മിനിറ്റ് റെസ്റ്റ് വേണമെങ്കിൽ പറഞ്ഞോളൂ. ഹലോ
ഹലോ സർ.
ബിനീഷ് മാഷ് 10 മിനിറ്റ് റെസ്റ്റ് വേണോ?
ആരാണ് സർ? ഗിരീഷോ?
ബിനേഷ് മാഷോട് ചോദിച്ചാണ്.
സാർ
10 മിനിറ്റ് റെസ്റ്റ് വേണം ചോദിക്കാം.
കുഴപ്പമില്ല, ആയിക്കോട്ടെ.
10 മിനിറ്റ് റെസ്റ്റ് എടുത്തോളൂ. നമുക്കിപ്പോ 15:30 15:40 മീറ്റ് ചെയ്യാം.
ഓക്കെ.